Hi, welcome back. Today I have a shop project for you, a toolmaking project. I built a super low profile dial test indicator holder for the CNC milling machine to indicate and pick up the location of bores, bosses and the edges of workpieces. And my solution on the manual milling machine is probably well known. It's the half moon shaped indicator holder, and here on the CNC I used to use a Noga flexible arm in a collet holder, but that took up fairly bit of C height, and my new solution only needs 37 millimeters from the collet nose to the end of the probe ball of the dial test indicator down here. So 37 millimeters. That's just 2 or 3 millimeters more than the height of the dial test indicator alone. So I think we can consider that low profile. And I already tried it out. It works quite well. I don't hate it. And it has a 6mm shank. If you decide to make one yourself, which you can because I'm going to put the drawings down in the description of the video, you can make, of course, the shank every diameter you desire. And also you can play around with the materials. I have chosen tool steel for all the parts, except the knurled nut and this handlebar here, which are stainless, but all of the parts will be sent out for plasma nitriding so they don't scratch, dent or wear from abrasion when you adjust it for size. So let's look at the drawings. Here we are in CAD, and as you can see I have a mock-up 3D model of a MAR 800S dial test indicator. This is the standard indicator that I use in my shop mostly, and that's also where I designed the indicator holder around. When I do something like this, I start out just by blocking out a very rough idea of what I want to achieve, and this is just a single body shank. Everything is one piece. Just get a super rough idea about the dimensions. The indicator is moving in one axis to adjust the radius. We have a shank here, and the shape of the body is already pretty much final. After I have it blocked out, I refine it into something like this. As you can see, the dial test indicator is held over a dovetail in this small clamp here, and the clamp is held to the entire body with a screw sticking through, washer and a knurled nut on the other side. Didn't model the knurling, of course. And that way you can adjust the size very neatly from pretty much 0, or the diameter of the ball on the dial test indicator, up to let's see, I think this is maximum, to 78 millimeters maximum circle diameter. The clamp is guided in this slot here. This is basically the only precision feature, because if you make this too sloppy, the fit between the clamp and this body, it will be annoying to adjust. One feature that I wanted to incorporate is an adjustment if the stem of the dial test indicator is not on center line, which it's very often not. It can be adjusted on some dial test indicators, but that's a royal pain. So why is that a problem? On larger diameters, it's no problem at all. Slight misalignment doesn't harm you. But once you get to smaller diameters and the ball of the dial test indicator hits the feature you want to indicate somewhat tangential or off to the side, you introduce some weird errors, and also picking up edges and corners gets extremely painful if it's not on center. So I made the shank as a separate piece from the body, which I would have anyways, because otherwise it would be annoying to make, but I put it on an eccentric shank, so you can adjust it. So when you look onto the face of the tool, you can adjust it to be exactly in line with the tip of the dial test indicator. And that's a feature that I have not seen on a single dial test indicator to this day. So I will just pretend that I have invented it. Okay, that's good. Also, to keep everything as low profile as I wanted, I made this funny looking cutout for the dial of the indicator here. Depending on the indicator you want to use, if you build this yourself, you might have to adjust this, or you cut away all the material here anyways. That's up to you if you want to build something like this. This is absolutely, I'm releasing the drawings. You can do whatever you want, just don't be a dick. Make 100 of them and sell them on eBay. It's absolutely cool if you build 5 for your friends for beer money, but just don't make a business out of them. That would be kind of a dick move. I pulled out the 2 drawings of the main components, which are the main body and the slider. Pulled out most dimensions, gave it some tolerance on important features, but these are not the final drawings. This is just me building a very rough prototype now to see if this even is a feasible tool to be used. I found a piece of tool steel 12312, which is a extremely nicely machining commercial heat treat steel, which also can be plasma nitrided very well. So if this tool fits the bill for me, I will just send it off for plasma nitriding and use it that way. And for the slider, I found a piece of Tulox 33, which is also a commercial heat-treated steel. It's far from being hardened, but it has some toughness to it. Also very well suited for nitrating. I like to have the overall dimensions to be clearly visible, so that I instantly know what size of stock I need to prepare. And I want to do this the way I'm going to cut this to size slightly oversized, and then I'm going to square it up completely. And then I remove any remaining material so we end up with the shape. I'm giving it some allowance here, about 2 millimeters. Okay, that's the cutoff. Important to mark the cutoff once we're done. What alloy it is, 12312. And here is our part. We also need to cut it to length. After cutting the stock, first thing to do is to square it off. I have a 30 millimeter high-speed steel 6 flute end mill in here. Kind of old school style of cutter, but these work quite well to this day. You just have to go relatively slow, otherwise you will burn them up, especially in a heat-treated material like this tool steel. So how do we square up something that has not a single square surface, especially in a vise like this, which is not exactly made for holding rough sawn stock? For the first setup, we drop the part as low as possible, and we want to press the part with one of the surfaces as solidly as possible against the fixed jaw, because this is a good reference. And the problem is, since this part might be slightly wedge-shaped from bandsawing, since bandsawing is not the most high-precision process, when we clamp it, you might notice it's hinging around the high spot, and this is very dangerous. You could now just torque down like a madman on the screw and hope that everything deforms and kind of clamps this block, but that's a very ugly situation and very dangerous. A very classic way to deal with this would be something like aluminium welding wire or a piece of copper wire. Since I have a piece of copper wire here, that's what I'm going to use. I like to bend a little L shape onto it so it doesn't drop down and rise constantly. And I just hang this over the moving jaw. One parallel, so the part doesn't drop down while I deal with it. Now when I move the jaw up, of course I cannot put this wire in the center because there is this huge V cutout for holding round stock. I could also use a piece of copper round stock, but that would constantly drop down. So doing it this way. There are about 1,000 ways to do this. A ball bearing with a flat surface ground onto it works also very well for this application, but showing different ways here. How you do it finally when you make parts yourself, that's up to you, of course. I rarely run cutters that big. Let's see. High-speed steel against a preheat treated tool steel. Let's go with 15 meters per minute surface speed. We have a cutter diameter of 30 millimeters. Gives us a speed of 160 RPM. Okay. And we have 6 flutes. 6 flutes. Let's see, 150 here. It's number of teeth, 6. And we go for a feed of 0.07 millimeters. I'm just pulling that number out of my butt. Gives us a feed of between 65 and 70 millimeters per minute. Okay, that's the speed setting, 160 RPM on motor speed 1 in low gear. And the feed, 63 millimeters per minute, also on motor speed 1 in the high feed range. So this should work out. And we start out by removing the mill scale side. Okay, so this cleaned up all the mill scale. Okay, with what we did now, we created one first flat surface on this rough sawn piece of stock. How we proceed on, we take this flat milled surface now against the fixed jaw and face mill over the top again. And this will create a second flat surface square to the first one. As square as our machine vise and the overall machine geometry is, of course. But still we have no parallelism, means when we clamp here with the vise, we're not sure where it's clamping. As you can see, it's hinging on the right side, means part is still not parallel, because we didn't put any effort in making it parallel yet. Just giving it a quick deburr. Doesn't hurt to use the file over the flat to knock off any burrs from the top surface. Just makes things a little bit more precise, or increases the chance to make things more precise, however you want to see it. Let's clean everything. The only drawback on these high-speed steel cutters, on these large ones, is you're cutting glacially slow. It's so slow compared to a carbide end mill, same size. So drop in the parallel again. Our first reference surface goes against the vice jaw, the fixed jaw. We bring in our vise. We use again the copper wire to give a defined pressure point against the part. Would you please go here? Yes. Give it a good gronk. The copper will and can deform into place. And now we just take a facing cut over the top again. This should give us two sides of the part being square to each other and be a flat-ish surface within themselves. Flat-ish because we're just milling here, not surface grinding. So knock off the burr. Now with two sides flat and parallel, we bring a third relationship into play, and that's parallelism. We put the part with one machine surface on the parallel and with one machine surface against the fixed jaw. And when we cut the top surface now, this will be parallel to the underside and square to the back side, hopefully. So again, since we're clamping on a sawn surface with the moving jaw, we need again something to define a pressure point against the part. Our copper wire here. Also, now we can check the parallel down here if it moves, and this is very freely moving. The part is not seated down. So now we take our preferred implement of striking. In my case, I prefer either the rawhide mallet or a copper drift to knock down parts on the vise. I do not like dead blow hammers for this purpose. I absolutely despise them for this kind of work. They do not give the right feedback for me as a hammering person. To know what's going on with the copper drift. I get a very good feedback. And the parallel should be tight to move side to side, and it should also not be able to hinge inward. Otherwise you know that only one side of the part is resting on the parallel and allows the parallel to hinge on one point, which we don't want. We want parallels. We want full contact with the parallel, which we got now. I'm still ignoring dimensions here. I'm just doing a squaring up procedure. Okay. That's the third side squared. Now we have two parallel sides and one side that's square to the two sides. Means we don't need the copper wire anymore. Knock off the burr. So since we cut with the parallel as a depth reference, now we can measure the part and enter the thickness of our part into the DRO. Okay, now we can check the thickness of the part and enter the number into our DRO. So this is 27.33, 27.32, 27.33. So let's enter 27.33 into the DRO. Means with the parallels I have in the vise and this setting and not changing the length of my tool, I can directly read the thickness of my part on the DRO now. One nice thing about having a DRO, makes life very easy in that regard. Drop in the parallel and the second one, because now the part is square-ish. I think I'm going to surface grind it later just for appearance and also because it's less prone to rusting if the surface finish is better. But in reality for this tool, it does not need to be hardened, it doesn't need to be surface ground. The inherent required precision on it is relatively low, so don't get too stressed out if you want to build this yourself and you don't have a surface grinder. Do a good clean mill job and it will be fine. So final dimension will be 26 millimeters. I'm going to mill it to 26.2 to give me some stock for surface grinding. Also the surface ground finish looks nice after nitrating. Okay, I'm about to cut the final thickness on this dimension to 26.2 millimeters. So I decided on 0.2 millimeters of allowance for grinding. That's enough to play around and that's little enough to not get annoying. And I just wanted to show you the behavior of the parallels in here again. So everything is clean, deburred, drop the part in. I don't do anything to it and I just clamp it. And both parallels are moving freely. Let's get a little bit clear of the end mill. And just by giving it a tap with a copper drift, it seats itself. The rear parallel is super tight and this one can be moved, but it's also tight, means the part is not dead square, which parts rarely are. This means that this lower surface is a little bit tilted like this in relation to this back surface. Not a big deal, probably well within 10 microns because it's still grabbing on the parallel here. But also notice how I use the copper drift when I knock the part down. I'm not letting it bounce off, I'm giving it, I'm doing this, I can't exactly describe what I'm doing, I'm just hitting and not letting it bounce back. Also, if you hit the part in the vise strong enough with a rawhide mallet, for example, you might even get the part to bounce off the parallel despite being clamped. I have seen that numerous times. You hit it hard enough and the parallels just get loose again. I don't want to do it here because I have the vise on the indexing head and I don't want to beat it to shreds. But I suspect most people have noticed that behavior at least once in their time as a machinist. So use the force input in your part to your advantage to seat them, and use it mildly, not to lose precision. Also, despite copper being soft, it can mar parts, even steel parts. You can leave marks if you're if you're a very dedicated hammerer of items. So be careful there. Robin has an interesting technique for seating parts. He's using a small hardened and ground block that he puts on the part he wants to hammer, and then uses, I think he has a brass drift and hits the ground block. It would look like this for Robin. He has a ground block here, and then doing this. That way he does absolutely not get any marring on his parts if the surface of the in-between part is clean and surface ground and doesn't have any burrs or chips on it. About a million things to consider when you square up stock. And there are other techniques. You can also grab the stock on very little depth in the vise and just walk an end mill around. Then you have to fight cutter deflection, of course. But we do that on CNC machines a lot. Also, when you clamp parts in a vise, how deep you clamp it will change its behavior on what relationship you will achieve. If you clamp a part very deep against the fixed jaw, like here, the squareness is overriding the parallelism. If you go very far up on the jaws, like this, you are mostly going for parallelism, because the fixed jaw has very little engagement on the back wall of the part, and that way you're only going for parallelism. That way you can get both parallels to make full contact even without the part being that square. So, so many things to consider, so many little things to tweak, even on something seemingly simple like squaring a piece of sawn stock. The rawhide mallet behaves different from the copper when I use this. I let it bounce off. Yeah, there is a lot of hammering technique here. Okay, right off the milling machine, let's check with a square against a light gap. It's hard to tell in the video probably, but this is really not terrible for right off the mill, using a fairly large cutter with a little bit of cutting pressure. It shows a little bit of light over here on the left side, but we can qualify this in a second over on the surface plate using the height gauge. I have a 10 micron reading indicator mounted to the measuring slide of my Tesa height surface gauge or height gauge, which has squareness tolerance to the surface plate of 2 microns something over 400 millimeters. So this can be used extremely well as a squareness checking device. And the way this works is we make sure everything is clean and seating well on the surface plate. We bring the dial test indicator down all the way. We move the work up against the dial test indicator to a convenient number, like 30. Then we just traverse the work by using the height elevation of the measuring slide. And this is well within 10, 15 microns, well 20. It's falling off to the side here, which we also qualified using the knife edge square. So those two, the measurement and the visual observation that we did, match up, which is always very nice. If you come up with two completely different results, you usually have a problem at hand with your methodology of measurements. I surface ground the outside to 50 micron oversize. I ground it a little bit oversize, so in case it moves when I do all my heavy material removal now, I have a little bit stock to play. or if I put a large dent or scratch into it, I can also clean it up on the surface grinder. I didn't show the parallel and square grinding on this part. I will show it on the slider that we're going to make after this part. It's always the same. You put it on a surface plate on the magnet, grind one side, flip it over, grind the second side parallel, grab it in a vise very deep to square it up, grind one side square to the other two, flip it around, put it on the magnet, grind the fourth side. That's squaring up four sides on a surface grinder. Surface grinder is extremely fast at making things very square. Absolutely not necessary for this part, but it's nice to work with stock that's already inherent, precise, so we don't introduce errors from the beginning. That said, this tool does not require any inherent precision from the way it works, but well, I like nice tools, especially if I can shop make them. And truth be told, there is no extremely low profile dial test indicator holder to dial in tools on CNC machines with limited C height, which surprises me because Swiss lathes exist like the Tornos R04, and I have no clue how you get a dial test indicator in there to dial in the tools, especially the live tools and drills. Somebody will hopefully tell me in the comments how they do it on these machines. I suspect it's highly painful. So the ends are not squared yet, so let's do this. If the thing you're working on is extremely square and parallel, like this piece that we just did on the surface grinder, you don't even need a hammer on the milling machine. So let's drop this part in the vise and just clamp it. And there is directly some drag on the parallels, and the drag is very even on both of them. If we go one step further and we use our strength, our body strength, and just put down 2 fingers on the part and press down a little bit. I'm not even, well, maybe, what's that, 50 newtons. Pressing down on the part a little bit, and the parallels are well put in place. Well, this real one wants to slide a little bit. Let's retry. Okay. The rear parallel is held in place. Well, I can't slide them with force, but they're well put in place. And that way I don't even need to hammer it down. And the way we square up the end now is we just drop this cutter down and do some side milling. Side milling doesn't leave very square parts, but good enough to be cleaned up on the surface grinder. And to be honest, for general shop use, it's also square enough. It's just me being nitpick. The sidewall finish of this end mill leaves a little bit to be desired. I think I used this previously in cast iron, so that already took its toll. That's why I dislike high-speed steel end mill these days. They wear down so fast. Okay, checking the overall length. 71.62. 71.6 and a little bit. Once again, I can enter that number into the DRO, and this will give me a direct reading of my part dimension. So I'll move it back. Of course, you have to think in the right direction. And this time, since my end mill is going to the left, I don't have to put it into negative space. If I was working to the right, cutting stock off the right side of the part, I would have to go into negative space. Also, there's a ton of deflection in high-speed steel cutters, with high-speed steel being only 1/3 the module of elasticity from carbide. Over on the surface grinder, squaring the ends of the block, I have a grinding vise with its side surfaces held on a magnetic chuck, and I have a 6mm carbide pin down here as a spacer to get my work off the magnet. Otherwise, if I drop the work down onto the magnet like this, it gets stuck and I can't pull it out vertically to the other side. So a round pin is a good thing here. So the device is inherently precise enough to do a moderate good job of squaring the ends. An alternative would be to use a magnetic V-block like this. Standing up, these are usually also made precise enough to do decent squaring, or a toolmaker block where you bolt your part against, or a 1-2-3 block, maybe 2 to form an angle plate to square apart. Many options on a surface grinder, or you don't use anything at all and do step grinding, which is a bit tricky when you square up the third side on a part like this. On a machine like this with limited spindle power, I like a peel grinding approach where you plunge down and take only shallow step over. This is beneficial on machines with a relatively lightly built machine frame and a spindle that's only 0.25 kilowatts and leads to very nice results. Also, this technique provides good material removal. Squared up the first side, I can just take it out, flip it over, seat it in the vise, drop it down onto the round pin, and to the second side. Now both sides should be square and parallel to each other and to all the other 4 sides. Now I can measure the length on the surface plate with the height gauge or with micrometers, enter the height in the DRO and grind it to final length plus a little bit allowance. Now we need to remove a lot of material. First we start, as you can see, we have this large cutout here in the top view. It's this area here that basically needs to get removed. Top view, like this. 7mm remaining. Let's do some layout lines. Seven and 16 from the front. These are just rough layout lines, so I know what's going on. And this projects down on the front of the part too, like this. And we have 12mm remaining over here, like this. And all of this material needs to vanish. So, like here, like here. We could just go to the mill, put in a roughing end mill and go to town. Or since we're fairly civilized, we can go to the bandsaw and bandsaw out most of the material. And we could even bandsaw this little bit in here too, when we stood it up vertically. But I will saw out this piece. Clamped it. I used a 1-2-3 block here on the side to square everything up. Shouldn't be necessary now that it's clamped. And we're good to go. Okay, I have to say it's the guided bandsaw with the slide is really nice. It takes out any skill requirement from bandsawing a straight line. All that's required is a good sharp bandsaw blade. Also, thank you to all who recommended corset toothed blades for the size of saw. I will look into what I can get here. Whoop. Part goes out. Let's clean the table before we, since we're clamping on finished surfaces, we have to be a little bit careful with chips imprintment. But all these jaws are nice and smooth surface ground. And it doesn't hurt to hit the table with a stone. It's not illegal to stone the table of your bandsaw. Okay, let's see. Here we go. There we go. Massive material removal in a few seconds. Well, a few minutes. And since I squared all of the blocks outside previously already, my cutoff is already squared on 1, 2, 3, 4 sides. Well, sometimes that's useful to have some stock that's already square. And if I only surface grind the other 2 sides and put this in a setup block drawer. So now we have this L shape, and now we could just mill away this lower portion, or we could bandsaw it out. I think we're going to bandsaw it for the heck of it. Okay, there we go. You hear when you make contact with the previously sawn surface because the engagement of the saw blade changes. It hits down here. Haven't done the final alignment of the table yet. So now we just need to do a second cut here. I'm not sure if this is faster than milling it, probably not, but I just wanted to give an idea of using the bandsaw for bulk material removal. I think this is more important if you have a very small hobby milling machine, like a benchtop X2 machine, where removing 1 millimeter of steel is already a chore. But you might have a porta band or something similar in a stand, or one of the import 4x6 bandsaws, and those can be utilized for material removal very well. There we go. That's all the bulk material removed. You saw me milling this flat and also the 2 vertical walls of this post. And after milling, I took it over to a surface grinder and I just cleaned up in this direction, then swung it around 90 degrees and cleaned up this way too, and tried to blend it half decently. Walked away a little bit over here. There is a little bit of warpage in the part, but Truth be told, I'm not going to bother with it. It's in the 5 micron region. As you can see, the blend line, the crosshatch of the grinding wheel is fading out here. It's making contact, and it's making contact here, and it's a little bit deeper here, the 90-degree way. And honestly, it doesn't matter for what this is. But once I hit it with some Scotch-Brite and clean everything up, this will give a very even overall finish, which will very nicely fare over time, especially once it's plasma nitrided. Next step will be to cut the full-length slot in here. That's this slot here that goes all the way through, and then there is a shorter through slot, 3.3 millimeter wide, where this clamping screw for the adjuster pokes through. So just found my dial test indicator, and this is how it will sit in here. Later we have to remove a bunch of material up here, which is this cutout here. So there is room for the dial test indicator to get close to the wall and have the dial not hit the wall here. I cut the slot in the part using a 4mm end mill, and I finished it to a size. So a 6.01mm gauge block with a nice loose sliding fit in there, and a 6.02mm gauge block stack. Wants to start, but gets tight immediately. So the slot is between 6.01 and 6.02 millimeters. I also built a gauge block stack with 6.015 millimeters, 50 micron larger than my small gauge block that I had before. And this is an extremely tight sliding fit with barely any wiggle. So 5 micron more than this, and it doesn't fit anymore. Just to give you an idea of how tight the slot is and fit. Next we need a slot that pokes all the way through the part for the clamping screw. And this is just a clearance slot for a screw to poke through. So I have a 3mm end mill here, carbide 2 flute. And I'm just going to plunge on both ends of the slot. Then I'm roughing out the material, and then I'm widening the slot to final width. That's too slow. Slot for the screws in there. The last two features that we need to cut is this hole here, which is basically a precision counter bore. This is a feature that I don't like very much. You will find precision counter bores on automation equipment a lot to use with tube dowels or centering rings, which are basically a piece of reasonably precise piece of tubing. Often they are centerless ground on the OD, and they are used to align parts and have a screw pass through the center. And that's a very annoying feature to make on a manual machine, because you have to use a boring head or a rotary table if it's a non-through hole. In this case, I need a precision counter bore because it aligns the shank that holds this entire tool in a collet. So I'm probably going to use a boring head here. And the second feature, which is also annoying, is this radius feature here. This is a 16 millimeter radius, partial radius on the end of this step. And this is just so it follows the curve of the dial test indicator. This could also be a straight line. You could just mill it in an angle or straight and just round everything over. Wouldn't look as nice, but be 100% functional. I want the radius because it looks a little bit more finessed. We have about 17 options how to cut this radius. One would be the CNC mill, probably the simplest one. One would be to find a 32 millimeter end mill, which I don't have. Probably, I will check. Or we can saw it away, rough it out with an end mill, and then finish the radius with boring head, or we can set it up on the rotary table and rotary mill this radius. Or we can make a fly cutter, or we could set it up on the lathe on a faceplate and turn this radius, which would be very exciting, which I'm not going to do. Or in a 4-jaw chuck and turn it. It's basically a boring operation. I mentioned the center point of the radius, it's basically here, so you would have to hold it in a 4-jaw chuck like this with the center of the machine being here. Then you could bore it with boring bar. Would look very exciting with this large overhanging mass. I'm not going to do that. I'm most likely going to do a rotary table motion here. I have decided to use the most obsolete way of cutting this radius. I put the XY compound chuck on my indexing head. This basically allows you to move the work on top of the rotary table to shift the center of rotation on your piece of work around. But first we need to align. I will start by aligning the work in the Y direction, drilling the one hole and boring it, and then we'll create the center of rotation for our radius, and then we will use the compound table to move the work to mill the radius. So that's the plan. I have a dial test indicator and a spindle here, and to align the work I can just use the indexing head. I'm just manipulating the hand wheel of the rotary table or the indexing head until my dial test indicator doesn't show any change. Well, shows a little bit of change here. Okay, that's within 10 micron. That's good enough for this demonstration or for this piece. So now I can change to an edge finder, pick up this corner of the workpiece. I always like to idiot check my 0 position once I edge found, and I'm just moving to 0, 0 and check if I'm eyeball centric over the corner I want to use as an origin. Just change to a drill chuck. Let's see if we have enough C height on this machine to use this cobbled together setup. Deckel FP1 is not exactly known for having a ton of C clearance. when using stacked setups. Okay, I want to do all the drilling and then I change to a boring head for the precision work. I want to drill the hole for the shank, and I also want to drill the center hole of the radius we're going to machine. But at the spot where the radius is there, or the center point of the radius is, there is no material. So I found a piece of scrap. This is just a piece of aluminum tooling plate. And I prepared, let's do a cooking show. I prepared this one earlier. Wow. And I'm using a toolmaker's clamp. Double checking if I have enough space for my hole. Toolmaker's clamp to hold the part in place. In some cases I prefer a toolmaker's parallel clamp over a canned twist clamp. For once you can very precisely set the pressure points. Secondly, they are very low profile, they don't stick out anywhere, and they're just a very nice simple tool, and you can crank the crap out of them with a cross pin and a real screw. Sometimes I see people use these very weirdly, not knowing exactly where to tighten them. So the basic idea on these parallel clamps is you adjust with this front screw here, your opening of your parallelism of the jaw, and for a quick adjustment you just do this, and you don't have to individually fumble around with the screws. So you get it roughly to size, and you use the front screw here to very lightly pinch your work, and you can still adjust everything if in that condition, and with the rear screw you tighten it. I have a brass shim on this side to not mar my work, and you always want to make sure that the jaws of these pliers are either dead nuts parallel or like this, so you get a pressure point on the tips and not somewhere here on the edge and mar the edge. So excellent tool. Many people despise them these days because they are a very old school tool, but they are cheap, they work very well. They're a very classic toolmaker item for when you have a stack up of plates, you clamp them together and drill and ream them together. Then this is the classic tool here. Of course, since I left a little bit of allowance on the surface, I have to adjust plus the allowance over, if the hole position did really matter. But in reality, this hole position is super uncritical since the shank of this tool is adjustable. But still, just saying, because otherwise somebody will tell me in the comments that I forgot to work with the allowance, which is absolutely true if I didn't think about it. Okay, one spot drill. And we're just going to drill and ream a 4mm hole here, so you have something to indicate on. Okay, that's our location hole for that we need later for cutting the radius. Now we will go back to this position and do our precision counter bore. It's a 3.3 millimeter through hole for an M3 screw. Oh. Yes, I have a 9mm 3-flute high-speed seal end mill. This will do. Let's drop down the speed to 400 RPM. Well, that's not 400. Okay, I'm using, when I do plunge cuts like this, I prefer to use the whole C-axis compared to using the quill. So at this point I decided to stop the video and make it a 2-part series because it's getting painful long. But I wanted to go into extreme detail about squaring the stock from a 6-side sawn piece of material to square, which I think I have never shown that detailed before, and I felt like there is a lot of detail to go into. Part 2 shouldn't take too long to edit. The drawings will be available down in the description of the video. Thank you all for watching, thanks for the support, and I'll be back.